Alright, so in this video we're going to be talking about complex numbers. And so I'm going to be going through the handout from our class website. Um, yeah, there's some really beautiful mathematics of complex numbers. Unfortunately, this video is not about them. This video is about just the nuts and bolts of complex number system. Okay, so we're going to be, we'll hit a few things along the way, but let's just get a quick definition here. Definition, if I can write. Definition, what is a complex number? Complex number, the complex number z equals a plus bi, where a and b are real numbers, and I is equal to, it's defined to be equal to the square root of minus 1. And so, just as a quick note, if you're in an engineering program, engineers tend to use J instead of I. Okay, so that's just something to keep in mind. So what are some implications of this definition? Number one is that if b is equal to 0, then we get all real numbers, right? And so therefore we can think of the complex numbers as being like a superset of the reals, right? The reals are contained within the complex number system. Okay. So just some examples. 5 plus 2i is an example of a complex number. If you don't work with them very often, maybe minus 5i is a complex number. You could even write like pi plus ei if you like, just to be kind of weird there. Now we know that a number like 3 is a complex number. Okay. We also, if we look at the powers of I, we'll see that they're cyclic. So I is equal to the square root of minus 1, right? So what is I squared? I squared would be minus 1. So what is I cubed? I cubed is minus 1 times I, which is minus I. And what would I to the fourth be? That's I squared squared, so that would be a positive 1, right? And then I to the fifth is equal to I, so I to the fifth is equal to I, and you're back to where you started, right? So then I to the sixth would be minus 1, I to the seventh would be minus I to the eighth would be 1, and so on. Good. And so then you're going to cycle through these numbers over and over again. All right. We can, so as we noted, a complex number contains two parts, and so we denote if z is equal to a plus bi is our complex number, is complex. Then the real part of z, we could say sometimes it's rez, sometimes it's actually spelled out, is just the number a, and the imaginary part of z, sometimes abbreviated as that, is the b. And notice that the imaginary part does not contain I. No I. Okay, so when we talk about the imaginary part, we're just talking about the real number part of the imaginary number. Okay. If that makes sense. Okay. For example, what's the real part of 5 plus 2i? That would be 5. What's the imaginary part of 3? That would be 0. What's the imaginary part of 3 minus I? That would be minus 1. Good. Okay, so that's the real part and the imaginary part. Good. Now, before we get into how to manipulate complex numbers, sometimes it's a good idea to visualize complex numbers. So let's see if we can visualize the complex number system. Visualize the complex number system. So the way we're going to do this is we're going to associate the complex number z, I guess associate the z, just associate z equals a plus ib with the ordered pair ab. And so therefore we can consider the complex number system in the plane, and in fact it's called the complex plane. So the complex plane is what you get when you do that. And the complex plane is denoted by a C with a line through it. And so if a plus ib is associated with ab, that means our point a plus ib can be plotted, right? A plus ib is associated with ab. Okay, and so this is the imaginary axis, this is the real axis. Okay, and so every number in the complex number system can be plotted like that. Good. Now, what's interesting about this is that we know that in the plane there are other representations, right? And so instead of representing things kind of in the Cartesian coordinate system like we've just done here, there are other representations. And so if I put my a plus ib here, a and b, we know that there's also something called, do you see what I'm going to write? The polar form, or polar coordinates, right? So this would be our r, right? And so let's go ahead and maybe I'll put the a and the b in the normal place here so we can focus in on this triangle. Good. And so theta is always going to be the angle, right, that's made with the positive real axis here. And so we always measure theta being rotating counterclockwise. Okay, and so it's the zero angle is here. Very good. Okay, so in this triangle then, what is the r and what is the theta? R is the square root of a squared plus b squared. And theta? Well, we can put theta for now. Maybe I'll write as a, just to pause here for a second, tangent of theta is b over a, right? This is normally how we would write things in the polar coordinate system, but you do have to be careful, right? Because your a could be 0, for example. Graphically, what's going on if a is 0 and b is not? If a is 0 and b is not, that means you're up here at pi over 2, right? And so you do have to be careful about this. Let's pause on that though for a second, because I don't want to get too far into that right now. But I did want to do is just to define a couple of things. So for the complex number, we say that the modulus of z, which is abbreviated as an absolute value of z, it's in the modulus, that's equal to the r up here, right, in the polar form of z, and so that is the square root of a squared plus b squared. Okay, and then the theta, the angle theta that makes up the complex number is called the argument of the complex number. So often we'll abbreviate it as theta equals arg z. Okay, and now we do have to be careful defining theta. So typically theta is taken to be in the interval from minus pi to pi. I guess we include point pi, right? But you have to figure out which interval you want your theta to be in, right? Because you could be talking about the interval from 0 to 2 pi, we're talking about the unit circle, right? And so right now we're talking about going from this as being minus pi all the way over to this as being positive pi, right? But you could be thinking of the circle in kind of normal terms as like this being 0 and then going around and this being 2 pi, right? Okay, but in any event, the idea is we want theta to be in the 4 quadrants, right? And so this is getting back to my original pause here, that if I take tangent of theta to be b over a, I'm going to run into trouble. And that's because, just as a reminder, we're going to take a bit here, problem. I'll put that in quotes. For tangent of theta to be 1 to 1, right, we restrict the domain to theta being between minus pi over 2 and pi over 2. And so that's a bit of a problem, right? Because that means, therefore, if you take theta to be the inverse tangent of b over a, right, and you look at where theta would be on the unit circle, that means that your calculator is going to run from this angle, pi over 2, to, well, it's going to be in these 2 quadrants, minus pi over 2. Right? So this is where this angle resides, in one of these 2 quadrants. Okay, and so in the next video we're going to talk more about that and see how we're going to fix the problem of having the inverse tangent only appearing between pi over 2 and minus pi over 2 as a 1 to 1 and onto function, right? And then we need somehow to get it all in 4 quadrants.